We have projects that span radiology, pathology. We do a lot of computational pathology work. We develop clinical tools like image viewers, and we actually have projects in mobile health as well. And one of my jobs as the director of the lab is to try to figure out how to put all these things together and tell a compelling story. In this talk, I'll be focusing on our work in prostate cancer, and I'll talk a little bit about one of our new image viewers that we've developed. So luckily, this is the second rotating prostate you've seen this morning. If you have that on your bingo card, congratulations. What you see obviously is the outline of the prostate, but here within the prostate, you see these three red regions, and these are what were drawn by our radiologists in magnetic resonance imaging space to denote suspicious regions for cancer. And then through those, you see little straight lines, and those represent biopsies that were taken of that suspicious region. And then the numbers associated with each of the lines represent the pathologist cancer grade. Okay, so the Gleason grade. And I show you this to give you kind of an idea of what our data sets look like. So we have the associated MR images, we have the radiologist contours, and we have the pathologist grades. And so this data set forms the basis of the work, a lot of the work we do. So one of the first things we did was we wanted to take those radiologist contours and train a model to do cancer segmentation in MR space. And the hypothesis here being that a model can segment areas suspicious for prostate cancer on MP-MRI. And the motivation here was to avoid unnecessary biopsies or guide prostate biopsies more accurately. And it was a pretty straightforward approach. We took a three-dimensional UNet model and trained it with the radiologist annotations, which I've shown in blue here. We had around 1,000 patients. We had to have a custom binary cross-entropy loss function to deal with the data imbalance. You can see our performance statistics on the lower right. We have an AUC of 0.95. That's misleading, obviously, given the data imbalance. There's far more normal voxels than there are disease voxels. Hopefully everybody can hear me okay, or we're doing an adjustment. Okay, all right, we're good. We have an average precision of 0.35, so much lower, and a precision at 80% recall of 0.4. So again, not great performance statistics. However, if you look at the images, if you compare our predictions in the red with the blue, you see we do localize to where the cancer is, but we have many false positives, and that's kind of the nature of the problem. We could do some post-hoc smoothing or something, but we didn't actually do that here. What we did instead was we got rid of the annotations. So generally, precise annotations are kind of a pain to deal with, and Thomas mentioned this a little bit. They're costly to produce. You can never produce enough of them. They're noisy, right? You're not going to get your subspecialist radiologist. You're going to get their fellow, and then you might get the resident that fellow recruited to draw the annotations. And often, I think I would argue they're not necessary. So our hypothesis for much of our work is that weakly labeled data, so data with no voxel labels or pixel labels, can be used to both detect and localize prostate cancer. And so one of the recent models we put together tried to explore, well, Thomas already talked about this. This is the framework we leverage called multiple instance learning, a very basic introduction. In our typical fully supervised classification scenario, we have instances or samples, and each one is directly labeled. So here you can see blue triangles are zeros, red triangles are ones. In a multiple instance learning scenario, instead of individual samples with labels, you have bags of samples with labels. So you can see here a bag with all blue triangles gets a 0, but if there's a single red triangle within that bag, it gets a score of 1. And so with enough data, and the right models, you can begin to learn the association between that label 1 and the red triangle within the PEG. So in the MR space for prostate, what we applied MIL, and it looks a bit like this. So we have our 3D NPMRI, and the overall label is derived from biopsy. And so it's the highest cancer grade assigned from the associated biopsy. We then tile that 3D NPMRI into little 3D cubes or patches. And then we pass each of these sources into CNN feature extractors to extract some, highly nonlinear complex features. And so we have this global branch and we have a local branch. Okay. On the local branch, we can add on an attention module. And so this is where the MIL kind of comes into play, where for each of these patches, we can learn a weight, and that weight is related to how important that patch is to making a correct classification for the overall prostate. We then append these two CNN features together, and we do our final Gleason grade prediction. And again, because we can do localization here with the local branch, we can spit out kind of this localization map that shows where the cancer is. So we trained this model with around 1,000 men. We did, again, Gleason grade group classification, which is pathology grading. We binarized between Gleason grade group 1, which is generally considered to be indolent cancer, versus anything higher. And you can see our performance statistics here. So we get an AUC with our best performing model of around 0.75. But what's maybe more important is our free response receiver operator characteristic curves, or FROC curves here, which show sensitivity versus the false positives per patient. And what I've shown in this graph is those lines stratified by Gleason grade. And you can see for the higher Gleason grades, we can have very high sensitivity with very few false positives per patient, which is what we'd want to see. And we have an example on the top right here, where you can see the red is what was outlined by the radiologist, and then the grayscale cubes are the attentions from the model. And what you can note is that we have good overlap. And an interesting thing is that in this particular case, the radiologist didn't actually annotate both lesions on both slices. And this really would have confused a model that was using these ROIs as ground truth. Excuse me. So one other thing I wanted to talk about in imaging is federated learning. And that's because yesterday we heard a lot about real challenges with generalization of models and bias in models. And it's something that was discussed in the last two talks as well. And with healthcare data, it's very difficult to overcome this problem because it's difficult to share data outside of an institution. Thomas showed a great paper that they published with data from 200 institutions. And whenever I see that, my mind is blown, because the administrative work to get that done is really incredible and very difficult to do. And not every institution can do it. And federated learning is a way to maybe get around releasing data. So we looked at a toy problem. We weren't interested in solving a difficult machine learning problem. We were just interested in studying federated learning. So this was UNET prostate segmentation. We took 100 T2 weighted prostate MRIs from 3 institutions, and each MRI was annotated with prostate contours by an experienced radiologist. And then the sets were divided into 80 training and 20 held out tests. And then we took 343 additional T2 weighted prostate MRIs from the Prostate X Challenge, which is an external data set. And here DICE, the DICE metric was our performance statistic. And that's just a measure of overlap between what you predicted and the ground truth. You can see this is from a recent paper that showed an overall DICE of 0.9. DICE scores are even higher for this problem, maybe around like 0.94. So for those who aren't aware, federated learning, what you do is you actually share your model rather than sharing your data. And so here you can see our 3 sites for UCLA, the NCI, and SUNY Upstate Medical University. And so what happened was each of our sites trained a local model on the private data and then sent that model to a federated server, where the federated server performs some weight aggregation of the 3 models. So it attempts to either average the weights or some other method of aggregating those weights. And then it pushes that global model back to the local institutions for further training. And that cycle continues of pushing the model back to the federated server and sending it back after aggregation until some convergence criteria. So here are our results. What I wanted to show is each row is a private model and a column is a private test set. And so if we see, for example, the NCI private model works the best on the NCI private test set data, which isn't surprising, but the federated model isn't far behind. And you can note the federated model does much better than either of the other 2 private models. We see a similar thing for the SUNY model. And then for the UCLA model, we again see a similar phenomenon, although the federated model does even a little better here. If we look at the overall test set, so not just the 20 for each institution, but all 60, we see that the federated model does the best. And then if we look at performance on the external Prostate X challenge data set, the federated model again does the best. And that's exactly what we want to see. No model was exposed to this data, yet the federated model does better than any of the 3 private models. And so I think federated learning will play a larger and larger role in training more generalizable models, especially in the healthcare space. So shifting gears to whole slide imaging, and Thomas already showed kind of the scale of digital pathology data. This is a long wedge resection. Thankfully, it's not mine, although I feel like it could be the last few days. And just to give you a sense of the scope, if you were to blow up this little pinpoint on the image, it would look like this level of detail. And we don't. My lab runs a GT450 scanner, so we can create one of these roughly every 32 seconds. And so, as Thomas mentioned, you need to reconsider your storage when you're doing digital pathology and your hardware compute as well. We don't have a similar scale setup, but we have had to make investments and build out. So again, I'm focusing on prostate cancer, and in the digital pathology space, our hypothesis was that a deep network could learn features that discriminate cancer and Gleason grade on histology using core level labels. And our motivation was to reduce the burden on the pathologist, to maybe offer quality assurance programs, and to discover new phenotypes. Here we had clinical prostate biopsies. This work is maybe a couple, 2-3 years old, I think. 830 patients and 20,000 biopsy slides. Again, we use an MIL approach, just like Thomas mentioned previously. You have a bunch of benign slides where the label is 0. You have a bunch of malignant slides where the label is 1. You tile up the slides, and again, with enough data, you can begin to localize where the cancer is on the malignant slides. So this model is a 2-stage model. It's multiple resolution, but it's similar to the one I showed in imaging. Basically, we tile the images at 5x resolution. So this is similar to what a pathologist might use for their initial sweep to look for cancer. We extract CNN features. We again have an attention module. We do cancer versus non-cancer prediction. And then for cancerous tiles, we do some additional sub-selection based on a clustering procedure. And then we zoom in on selected tiles to 10x, so a higher resolution as a pathologist might use. And we do cancer grading. And And again, we have the same sort of pipeline with the CNN extractor and an attention module, and we eventually do grading. So if you look at the results of this, again, we don't have actual labels to compare to, but luckily our pathologists really like to use markers even on the tissue, despite my pleading with them not to. So if we compare the attentions from the model with the markers from the pathologist, we see a pretty nice alignment between what the model's seen and what the pathologist saw. Again, we can look at other ways to visualize the data like TS&E plots. For those who don't know, it's just a nonlinear dimension reduction technique with the goal of projecting high dimensional data into low dimensional space, so such that your similar samples stay closer together. So on the lower left here at 5x, you can see we actually get good separation between our benign tiles in black and our high grade and our low grade tiles. So that's kind of expected. And then if we zoom in and if we look at those deep CNN features at 10x, we can still get the separation between benign and cancer, but now we can start to see separation between low grade and high grade. So we use these plots just to kind of give us some assurances that the model is learning what we expect it to. Here are our raw results. Again, Thomas already showed performance statistics for this task. Ours are similarly good, 0.98 AUC with an average precision of 97.4. I think maybe a little more impressive than just cancer diagnosis is the cancer grading. So in our confusion matrix here, it's kind of interesting because again, as overall cancer detection is quite high, but you see grading is a little lower in terms of performance. But what's important to note is that you're only off the diagonal by 1 for any of these pretty much. That's where most of your probability lies. And this is a subjective task even for pathologists. So being off the diagonal by 1 isn't that bad. And we haven't done the actual study, but inter-rater agreement from pathologists on some of these grades is around like 0.65. So this result was not unexpected and I don't think is necessarily bad. One other thing we're doing more recently in prostate cancer is looking at the problem of prostate biopsy undergrading. So there's significant cancer upgrading from biopsy to radical prostatectomy that results in both under and over treatment. So because this phenomenon of undergrading is known, if you get a prostate biopsy back and it's low grade, you might know the statistic that say 30% of people with low grade actually have higher grade. And so you might pursue treatment even if you don't need to, versus if you get that low grade and you trust that it's low grade, but it's actually higher grade prostate cancer in there, you might undertreat. And so our hypothesis here is that some prostate cancers exert a field effect on surrounding tissues that is detectable via computational pathology. I've kind of outlined that diagrammatically here, where we can see 3 systematic biopsy cores that were taken. All of them missed the 2 cancer lesions. But if our hypothesis that there's some field effect exerted by this cancer is true, and it extends to the biopsy locations, we could infer that cancer exists if we could detect that signature with computational pathology techniques. And so this is very early stage work. We're just kind of using various methods on our whole mount data. So this is a prostate whole mount. We do it at UCLA. Most places do not do whole mount. What it is this is the prostate that's been removed from the body. And at UCLA, we slice it like a loaf of bread. Many other places will actually cut it into quarters or do some other type of sectioning. But because we do this, we can actually outline very nicely where the prostate cancer is. So on the top left here, this is what the pathologist drew. And beneath that, we had them draw kind of a tighter boundary rather than what they just sort of do casually clinically. And that's in the darkest red color. And then we extended that border with the 2 lighter shades of red to kind of create a field effect zone that we call near normal, in which we would expect to see field effect. And then we had the pathologist draw two faraway normal zones. These are the blue zones here, where we expect potentially there to be no field effect or lesser field effect. And one of the first things we did on the bottom right here is to look at just radiomic features within these three zones. So tumor, near normal, and far normal. And what we see are different radiomic signatures. So we actually did nuclei segmentation. So these are kind of nuclei features. But you can see near normal and far normal have different signatures. So we think there's something here, but it's been a real challenge to find, but we're still working on it. The other figures here, again, because we're not going to get a pathologist to do this for 300 whole mounts, it's extremely tedious. We were applying our own machine learning models that I just showed. So the top right is an example of our cancer probability map. So you can see we do a pretty good job, but then we're trying to figure out, can we use this to look for regions of possible field effect? So in the middle bottom image here is what you see. It's an uncertainty map. So basically we ran our model under different conditions and looked at the variance in the probability of predicting cancer. And what we see is high sort of uncertainty around the margin of the cancer in certain places. And so that tells us there might be something going on there. And so we're looking more into that at the moment. Okay. So one last thing. And these individuals at the top, these are all the folks in the lab who have really helped make these projects happen. So a slide viewer that we've been working on. So again, this is the example of our prostate biopsy. And each of these lines, again, represents a biopsy core that's taken. You can think of it like a cylinder. And what we do is we take that core, we mount it, and then as Thomas shows, we use a microtome to slice it lengthwise, like the opposite way you would slice a loaf of bread, to generate these very thin ribbons that the pathologist will then look at. And so each of these cores takes 3 glass slides, and each slide has 2 ribbons. It used to be that each slide had 3 ribbons, but our pathologists were getting too tired. And they're getting tired because what they have to do is swap glass slides on their microscope repeatedly, because this is actually 3-dimensional structure you're looking at in the prostate. And what they're trying to do is follow glands through the Z dimension to see how that gland might change through space, because that will influence the cancer grade that they assign to this patient. And so they have to put a slide on, zoom in, find a gland. If it looks suspicious and that they might need to look at it on a different slice, they need to pan over to the other ribbon and try to find that same gland. And it's extremely time consuming. At UCLA, we do 12 systematic cores, as most places do. And this is the number of slides that those cores would produce for a prostate biopsy. We then also do targeted. So we have an additional 6 cores typically. And the pathologist has to look at all of these. We have very high prostate biopsy volumes at UCLA. We do many, many a day. And what this results in is very fatigued pathologists. And I know a few GU pathologists, and they always seem tired, frankly. So what we've done is we've developed this alignment framework, which is kind of cool. It's based on CYP descriptors and a graph neural network, but we feed in our ribbons and we align them to a reference ribbon. And you can imagine what we might do then is we can stack them together and put them in a digital viewer. And what this actually looks like then, so for prostate biopsy, we can load it up and scroll through. And now instead of having to pan and zoom, they're registered together. So with a keyboard shortcut, you can actually zoom in and then scroll. So if we zoom in, maybe on one of these glands here, there we go, and then scroll through. Now you can follow the gland through the volume much easier. And so right now we're in the process of doing a time study and equivalency study for this viewer. You can also use it in other things. We're actually testing it in multiple areas. So this is a kidney biopsy, and here, what's less important is we also have a little glomerulus detection algorithm running here. What's less important is the 3D structure, but rather looking at the tissue under different stains. And so again, the viewer helps to do that much more quickly. So we've been doing the study for a couple months now. Hopefully we'll have some results soon that we can share. So to summarize, strong supervision is not required to get good AI results that I would argue have the potential for clinical utility. Prostate imaging AI can support CAD and biopsy targeting. I'd say prostate pathology AI is poised for a much larger role, and I think Thomas already convinced you of that. There's some evidence for detectable histological field effect, but more work is needed. And new viewing tools in digital path can drastically speed up workflows, and even more so with AI. So with that, I'd like to thank everybody for their time and really acknowledge my students and staff and postdocs, as well as the faculty collaborators, and be happy to take any questions.
I have two.
Uh-oh.
As a Corey, fabulous work as always. On the federated learning side, could you differentiate what was the reason that the federated model was better? Was it just more data, or was it the diversity between the different labs? And the second one, how could you make sure that all sites actually use the same machine learning stack for training the models?
Yeah, so I think to your first question, it's probably a bit of both, honestly. We only had 100 cases from each site, which for prostate segmentation isn't bad, but you might want more. So I think it was the amount of data that probably helped the federated model. And then I think the diversity of data probably helped as well. That's a little more difficult to suss out. You know, if you recall, there was a weird phenomenon with the UCLA model versus the other models that probably had to do a bit with the data. Then in terms of using the same ML stack, so here we had a controlled federation in which we were able to dictate what was used, and we had sort of good actors in the federation. I think with larger federations, that becomes more of a problem. We haven't had to deal with that yet. I know there are technologies out there being developed by NVIDIA and companies like Rhino Health that are trying to productize sort of FL stacks, but that wasn't an issue for us. I don't know if that addresses your question.
Okay, thank you so much.
Thanks, everyone.
Joining via Zoom. Okay, our next and final speaker this morning is Stephanie Harmon from FBI. So Stephanie received her PhD in medical physics from the University of Wisconsin in 2016. In 2017, she joined Leidos Medical Research as a postdoctoral scholar within the molecular imaging program at the National Cancer Institute before transitioning to a staff scientist in 2020 in the newly formed AI resource group. The group supports NCI investigators in the development and deployment of novel medical imaging AI applications. So thank you for joining me and welcoming Stephanie this morning.
We're going to wait one moment to switch the screen over. So surprise, surprise, I'll be talking about prostate cancer applications as well, hopefully with a little bit different twist. And I'll be talking about how we're trying to loop in